Picture this: a cat sits inside a sealed box. Because of a precisely arranged quantum device, the life of this cat is tied to the fate of a single subatomic particle. According to the bizarre rules governing the quantum world, that particle can exist in a state of limbo, a combination of possibilities, until someone looks at it. So, what does that mean for the cat? Is it alive? Is it dead? The unsettling answer proposed by physicist Erwin Schrödinger nearly a century ago is that the cat is both. Simultaneously alive and dead, a living paradox trapped in a state of pure potential. This is the strange world of quantum superposition, where things don't have to be one way or the other until the very moment they are observed. But then something startling happens. The box is opened, a glance is cast inside, and in that instant the fuzzy, uncertain reality collapses. The cat is definitively, unquestionably, either alive or dead. The wave of possibilities crashes into a single, solid fact. This isn't just a thought experiment about a feline. It is a profound puzzle about the very nature of existence itself. Does reality only become real when we look at it? Welcome. This is the central, mind-bending mystery of quantum mechanics, a puzzle so deep it has troubled and fascinated the greatest scientific minds for generations. It's called the measurement problem. How does our definite, concrete, everyday world, where chairs are solid, objects are in one place, and cats are very much either living or not, emerge from the ghostly, probabilistic fog of the quantum realm? For decades, this question seemed almost philosophical, a strange quirk of physics that might never be fully solved. But what if the answer isn't found in some mystical act of consciousness? What if the collapse from possibility into reality isn't triggered by a human observer, but by a relentless, pervasive process that happens all around us all the time? This process is known as decoherence, and it may very well be the key to understanding why we experience a single, stable universe. In this video, we are going to embark on a journey to the frontier of our understanding. We will explore how decoherence solves the measurement problem, not with a dramatic collapse, but with a quiet, inevitable fading away of quantum possibilities. We'll see how the simple act of a quantum particle bumping into the trillions of atoms in the air around it is enough to force it to choose a state, to solidify into the world we know. This isn't just about explaining a laboratory phenomenon. It's about deciphering the fundamental code of our reality. It challenges our most basic assumptions about what is real and how we come to know it. So prepare to have your perspective shifted. We are about to dive into one of the most extraordinary ideas in modern science, an idea that explains how the fuzzy, multiple realities of the quantum world give way to the singular, definite reality we all share. The journey from Schrödinger's hypothetical cat to the solid ground beneath our feet begins now. To truly grasp the profound puzzle at the heart of this discussion, we have to step away from cats and boxes for a moment and look directly at the bedrock of reality at its smallest scale. In the quantum world, the rules are not the rules we know. An electron is not like a tiny, hard marble. Instead, it's more like a cloud of potential, a set of probabilities spread out in space. Physicists describe this strange state using a mathematical entity called the wave function. This wave function doesn't tell us where the electron is. It tells us the likelihood of finding it in any particular place if we were to look. Until that moment of observation, the electron effectively exists in a superposition of all its possible locations, a ghostly blend of here, there, and everywhere in between. This isn't just about location. A particle can be in a superposition of spinning clockwise and counterclockwise at the same time, or being both energized and relaxed. It exists in this blurred, unresolved state of multiple realities coexisting peacefully. The baffling shift occurs the instant we try to measure it. The simple act of setting up a detector to check the electron's position causes a dramatic and instantaneous change. The wave function, which was once a sprawling map of possibilities, seems to vanish. In its place, we get a single, definite result. The electron is now incontrovertibly here and not anywhere else. This sudden transition from a fog of maybes to a concrete this is what physicists refer to as the collapse of the wave function, and here lies the core of the quantum measurement problem. Why does this happen? What is so special about a measurement that it forces the quantum world to make up its mind? Is it the conscious awareness of a human observer that causes the collapse? Or is it the physical interaction with the measuring device itself? This creates a profound schism between two realities. On one side, we have the quantum realm, which operates on probability and potential, where things can be in two places at once. On the other side, we have our classical, everyday world, which appears stubbornly definite and predictable. A baseball is always in one specific place in the outfield. It is never in a superposition of being caught and dropping to the ground simultaneously. The measurement problem is the giant, unanswered question of how we get from the weird, wavy, probabilistic quantum world to the solid, singular, clockwork world we experience every day. It's the disconnect between the rules that govern the tiny building blocks of the universe and the rules that govern the universe those blocks build. For nearly a century, this has been the most glaring gap in our understanding of physics. A paradox that suggests our very act of looking at reality might be what creates it. Faced with this bewildering split between the quantum and classical worlds, the first and for a long time the most influential solution came from a group of physicists centered around Niels Bohr in Copenhagen. Their interpretation, quite boldly, proposed that we should simply stop asking why the wave function collapses and instead accept that it just does. In the Copenhagen view, the collapse is not something to be explained by deeper processes. It is a fundamental, axiomatic rule of nature. The act of measurement itself is the trigger, an irreversible event that forces a quantum system to abandon its ghostly superposition and pick a single, definite state. This framework introduces a critical, and some would say troubling, division in the universe. On one side, you have the quantum system, which behaves according to the wavy, probabilistic Schrödinger equation. On the other side, you have the measuring apparatus, be it a Geiger counter, a photographic plate, or a human eye, which must be treated as a separate classical object. The Copenhagen interpretation insists that this classical device is not described by quantum mechanics. It exists in a different category, and its interaction with the quantum system is what causes the sudden leap from probability to reality. The role of the observer, then, is not necessarily about consciousness, but about the necessity of using a large classical instrument to interact with the tiny quantum world. The moment information about the quantum system is recorded by this classical apparatus, the wave function collapses. Yet, for all its historical importance, the Copenhagen interpretation leaves several profound questions uncomfortably unanswered. Its most significant weakness is its vagueness on the central issue: what exactly qualifies as a measurement? Where is the boundary between the quantum and the classical? Is a single atom a classical device? What about a complex machine made of billions of atoms? Or does it require a conscious being to finally read the result? The interpretation provides no clear line, creating what's known as the Heisenberg cut, a seemingly arbitrary point where the quantum rules stop and classical certainty begins. This introduces a kind of duality into physics, suggesting that the universe operates by one set of rules for small things and a completely different, incompatible set of rules for large things, without explaining how or where the transition happens. For many, this felt like a philosophical surrender, an admission that our most fundamental theory of reality has a mysterious, undefined event at its very core. The stage was set for a new, more mechanical explanation, one that would do away with the need for a special classical realm and instead show how the definite world emerges naturally from the quantum fog through countless tiny interactions. Dissatisfied with the philosophical hand-waving of the Copenhagen interpretation, a brilliant and unorthodox graduate student named Hugh Everett III proposed a solution so radical, so all-encompassing, that it was largely dismissed for years. His idea, now known as the many worlds interpretation, begins with a simple but profound declaration: the wave function never collapses. There is no special measurement process, no mysterious transition from quantum to classical. Instead, Everett insisted that the Schrödinger equation, the fundamental law describing the evolution of quantum systems, applies to everything, not just to electrons and atoms, but to measuring devices, to the scientists using them, and to the entire universe itself. So, what happens when we open Schrödinger's box in Everett's view? The quantum entanglement between the radioactive atom, the poison vial, the cat, and the observer does not resolve into a single outcome. It continues to evolve. The superposition, rather than collapsing, simply enlarges. The single universe we started with branches into two. In one branch, the atom decayed, the poison was released, and the observer sees a dead cat. In the other, perfectly real branch, the atom did not decay, the cat is alive and well, and the observer sees it meowing for its breakfast. Both outcomes happen. Both realities exist. What we perceive as the single, definite result of our experiment is merely our subjective experience within one specific branch of an endlessly dividing multiverse. There is no paradox because every possibility is realized somewhere. This framework elegantly eliminates the arbitrary Heisenberg cut by making everything quantum. There is no longer a separate classical realm. The apparent definiteness of our world arises not from collapse but from a process called decoherence, which we will explore in depth shortly. In essence, the different branches of the wave function cease to interact with one another. They lose their ability to interfere. From the perspective of an observer within a branch, the other branches become completely inaccessible, as if they never existed. The universe appears classical and definite to us simply because we are trapped, for all practical purposes, within our own specific thread of reality. The implications of this idea are, to put it mildly, staggering. Every quantum event, no matter how small, an electron spinning one way or another, a photon reflecting or passing through glass, triggers a branching. The multiverse is not a static collection of alternate realities. It is a constantly flowering tree of possibility, splitting with every quantum decision. This means there is a universe where you never watched this video, and another where you are already an expert on decoherence. A universe where every conceivable historical event unfolded differently, and a near infinity of universes where the laws of physics themselves are subtly altered. While this interpretation solves the measurement problem with breathtaking mathematical simplicity, it does so at the cost of an almost incomprehensible cosmic extravagance, suggesting that reality is far vaster and stranger than we could have ever imagined. While the many worlds interpretation offers a mathematically elegant solution to the measurement problem, it immediately runs into a formidable wall of criticism. The most significant objection is not about its logic, but about its relationship to the very foundation of science, empirical evidence. How can we possibly test a theory that proposes the existence of an infinite number of universes that are, by their very definition, completely inaccessible to us? If an idea cannot be falsified, that is, if there is no conceivable experiment that could prove it wrong, then many scientists argue it steps out of the realm of physics and into the domain of metaphysics or pure philosophy. For all its appeal, many worlds seems to posit an unimaginably vast multiverse without offering a single shred of observable proof that these other branches are real. This creates a deep unease, as it appears to explain everything and yet predicts nothing that we can measure in our own solitary branch of reality. This issue strikes at the heart of a principle known as Occam's razor, a centuries-old guideline for scientific reasoning. In simple terms, Occam's razor suggests that when you have multiple competing explanations for a phenomenon, you should prefer the one that makes the fewest new assumptions. Proponents of the Copenhagen interpretation, for all its vagueness, could argue that it only assumes one mysterious event, the wave function collapse. The many worlds interpretation, however, makes an assumption of astronomical proportions. It asserts that every time a quantum event has more than one possible outcome, the entire universe splits, creating a near infinite number of copies of every person, planet, and galaxy. To many, this feels like an extreme violation of parsimony. You are asked to believe in an almost limitless multiplication of entities simply to avoid the paradox of wave function collapse. Critics contend that this is not an elegant solution, but an extravagant escape hatch, replacing one mystery with a far grander and utterly unverifiable one. Furthermore, the interpretation leads to some deeply counterintuitive and for some deeply unsettling consequences. If every possible outcome happens in some branch, then there are branches where you make every terrible mistake you ever avoided, and branches where versions of you achieve every dream you ever had. This can seem to trivialize our choices and experiences. If everything that can happen does happen, then what is the meaning of the path we actually follow? The uniqueness of history, the significance of our decisions, seems to dissolve into a sea of infinite alternatives. While this is more a philosophical concern than a scientific one, it highlights how the theory pushes against our deepest intuitions about identity, responsibility, and the nature of existence itself. For decades, this lack of testability left the many worlds interpretation in a kind of scientific limbo. It was a fascinating footnote, an intriguing but ultimately speculative idea discussed more in philosophy departments than physics labs. The pressing need remained for a mechanism that could explain the appearance of collapse, the definite world we see using only standard physics, without invoking conscious observers or countless unseen universes. The scientific community was hungry for a bridge, a tangible process that could show how the quantum world's blurry probabilities naturally give way to classical certainty through ordinary physical interactions. This set the stage for a more grounded, less extravagant explanation, one that would emerge not from rethinking the entire cosmos, but from carefully studying how quantum systems interact with their environment. The answer was waiting to be discovered in the countless random collisions that happen every moment all around us. This brings us to the pivotal breakthrough that offers a way out of this philosophical impasse, a concept that provides a physical mechanism for the emergence of classical reality without invoking consciousness or countless parallel worlds. The key lies not in looking inward at the observer, but outward at the environment. Every quantum system, whether it's an electron, a cat, or a measuring device, is never truly isolated. It is constantly bathed in a sea of particles and energy. It interacts with photons of light, molecules of air, and even the faint background hum of the universe's leftover radiation. This constant, uncontrollable chatter with the outside world is the engine of a process called decoherence. So, what exactly is decoherence? In simple terms, it is the irreversible loss of quantum coherence. Coherence is the special property that allows a quantum system to exist in a superposition, where its multiple possible states can interact and interfere with one another, like overlapping waves reinforcing or cancelling each other out. Decoherence is what happens when this delicate interference pattern is destroyed. It's the process by which a quantum system loses its quantumness and starts to behave in a classical, predictable way. The crucial insight is that this doesn't happen because of a grand, mysterious collapse, but because of the cumulative effect of countless tiny, random interactions with the environment. A powerful way to visualize this is to think of a perfectly still, mirror-like pond on a windless day. The surface is so calm that you can see a perfect, clear reflection of the sky above. This pristine pond represents a perfectly coherent quantum system, where the wave function's possibilities are cleanly defined and can interfere with one another. Now imagine a gentle rain begins to fall. Each raindrop is like a single interaction with the environment, a photon bouncing off an electron, or a molecule of air bumping into an atom. As the raindrops patter onto the pond's surface, they create ripples. At first, the reflection might just waver a little, but as the rain continues, the surface becomes a chaotic jumble of intersecting waves. The clear, single reflection of the sky shatters into 1,000 fragmented, shimmering images. Soon, the original coherent picture is completely lost, replaced by a blurry, indistinct mess. The rain hasn't created a new reality. It has simply drowned out the signal of the original one by adding an overwhelming amount of random noise. In exactly the same way, the environment acts as a permanent, pervasive rainstorm on the quantum world, constantly measuring it and scrambling its delicate superpositions. This environmental interaction is relentless and effectively instantaneous for any object large enough for us to see. For a tiny particle like an electron, it might take a fraction of a second to become entangled with its surroundings. But for something as large and complex as Schrödinger's cat, or even the dust mote floating in your room, decoherence happens faster than we can possibly measure. The countless trillions of atoms in the air and the endless stream of photons at room temperature are continuously observing the system, recording information about its state. This process does not cause the wave function to vanish in the Copenhagen sense. Instead, it causes the different possibilities within the superposition to become entangled with different states of the environment. The alive cat state becomes correlated with one set of air molecules bouncing off it, while the dead cat state becomes correlated with a different set. Once this information about the system state has leaked out into the environment and spread too far to be recovered, the superposition is, for all practical purposes, gone. The quantum interference between being alive and dead becomes impossible to detect. From our perspective, the cat is now definitively one or the other. Decoherence explains the appearance of collapse by showing how quantum possibilities become so hopelessly entangled with the wider world that they can no longer be distinguished. But how does this environmental noise actually perform its magic? To understand the mechanics of decoherence, we need to look a little closer at what a superposition really is. Think of a quantum particle in a superposition of two locations, say, being both here and there at the same time. This isn't just a 50-50 chance, it's a genuine coexistence. The particle's wave function has a specific phase relationship between the here part and the there part, much like two perfectly synchronized waves in the ocean. This phase relationship is what allows for quantum interference, the ability for these possibilities to either reinforce or cancel each other out, creating the unique, wavy patterns that define the quantum world. It is this delicate, precise correlation that is the essence of quantum coherence. Now, imagine this delicate quantum system, poised in its balanced state, is suddenly hit by a single photon from the surrounding environment. This photon doesn't need to be part of a formal scientific experiment. It's just a random particle of light zipping through the room. When it collides with our quantum system, an interaction occurs. The way the photon bounces off or scatters will be different depending on whether the system is here or there. In that moment, the photon becomes a tiny witness. It carries away a minuscule piece of information about the system's state. Crucially, the photon becomes entangled with the system. The overall state is no longer just a superposition of the system. It is now an entangled state of the system and the photon. We have a reality where the system is here and the photon scattered in one way, and another equally real branch where the system is there and the photon scattered in a different way. This single interaction might not seem like much, but the environment isn't sending one photon. It's sending a ceaseless, chaotic storm of them. Air molecules are constantly bumping into the system. The cosmic microwave background radiation is gently bathing it, and thermal vibrations from the system's own structure are jostling it incessantly. Each one of these trillions upon trillions of environmental particles acts as a separate, random measurement device. Each one takes a tiny, irreversible snapshot of the system's state and flies off into the universe, carrying that information away forever. This is the core of the process, the phase relationship between the here and their states. The precise synchronization that allowed them to interfere is exquisitely sensitive. As the system becomes entangled with more and more environmental particles, the information about its phase gets spread out or delocalized across the entire environment. It's like trying to maintain a secret when 1,000 different people have each overheard a different part of the story. The original, coherent message is lost in the noise. The different branches of the superposition become correlated with vastly different and now independent states of the environment. The here state is tied to one specific configuration of billions of scattered photons and air molecules, while the there state is tied to a completely different configuration. Once this entanglement has spread far enough, the quantum magic is gone. The possibility of seeing interference between the here and their states becomes practically zero. To see such interference, you would theoretically need to reverse the interactions to gather up every single photon and air molecule that ever interacted with the system and measure them all in perfect correlation to reconstruct the original phase relationship. For any object larger than a few atoms, this is an impossibility of staggering proportions. The information is lost to the universe effectively for good. From the perspective of any local observer, the superposition has been destroyed. The system now behaves as if it is in a classical mixture of probabilities. It has a 50% chance of being found here and a 50% chance of being found there, but it is no longer truly both at once. Decoherence hasn't collapsed the wave function in the Copenhagen sense. It has simply scrambled the information contained within it so thoroughly that the system is forced to appear classical. It explains why we never see a baseball in two places at once. It is constantly being measured by the environment, locking it into a single, definite location almost instantly. Now we arrive at the most profound and subtle point in our entire journey. The critical distinction between what decoherence actually does and the classic idea of wave function collapse. It's a distinction that is easy to miss, but getting it right changes everything about how we understand reality. The Copenhagen interpretation tells a dramatic story. A measurement occurs, and the wave function collapses instantly and irrevocably into a single, definite outcome. The cat is either alive or dead, and all other possibilities are annihilated. Decoherence, however, offers a much quieter, more gradual explanation. It does not cause a single reality to emerge by destroying the others. Instead, it explains why, from our limited perspective within the universe, it appears that only one reality exists. Think of it this way. Decoherence is not a pair of scissors that cuts away the branches of possibility. It is more like a dense, impenetrable fog that settles between them. The process of environmental interaction doesn't make the other branches of the wave function vanish. It simply makes them permanently invisible and inaccessible to us. In the language of the many worlds interpretation, all the branches continue to exist, evolving forward in time. But decoherence ensures that these branches lose their phase coherence. They can no longer interfere with one another. They become like parallel railway tracks that never meet. From the window of your train, you only see the single track you are on. The other tracks, though real, are separated from you by a wide, uncrossable gap. The fog of decoherence is what creates that gap, making the other branches effectively non-existent for any observer confined to their own branch. This leads us to one of decoherence's most important contributions, the selection of what physicists call pointer states. The environment doesn't just randomly scramble a quantum system. It preferentially selects certain states to survive its relentless noise. These pointer states are the states that are most robust, the most stable against environmental disruption. For a macroscopic object like a book on a table, the pointer states are clearly defined positions. The environment, through countless collisions with air molecules and photons continuously, measures the book's location. A superposition where the book is in two places at once is fantastically fragile and decoheres almost instantly, but the state where the book is sitting squarely on the table is extremely stable. The environment constantly confirms this fact, locking it into place. This is why the classical world is dominated by objects with definite positions. It's not because superposition is impossible, but because superpositions of position are the first thing to be destroyed by decoherence. Other properties, like the total energy of an object, can also be pointer states, remaining well-defined while more delicate quantum properties fade away. So, what does this mean for our poor cat in the box? Decoherence provides the physical mechanism that makes the cat behave classically long before we open the box. The cat, the vial of poison, and the radioactive atom are all immersed in their environment. The moment the quantum event occurs or doesn't occur, that information is imprinted onto the cat's physical state. Is its heart beating? Are its lungs breathing? This information is immediately broadcast into the environment through the cat's body heat, the air molecules it displaces, and the subtle sounds it makes. This process of environmental encoding happens in a tiny fraction of a second. By the time an external observer even thinks about opening the box, the cat has already been forced into a state that is, for all practical purposes, either definitively alive or definitively dead. The superposition has been reduced to a classical mixture by the fog of decoherence. The act of opening the box and looking inside doesn't cause a collapse. It simply allows you to discover which of the two pointer states the system has been in all along. You are reading the headline that was already written by the environment's relentless interactions. This framework elegantly bridges the quantum and classical worlds without any mysterious exceptions. It shows that the definite world we see emerges naturally from the quantum world through ordinary physical processes. There is no need for a special classical realm or a conscious observer to trigger a collapse. The solidity of our reality is a consequence of our immersion in a noisy environment. For any system large or complex enough to interact significantly with its surroundings, decoherence acts with breathtaking speed, making quantum weirdness a transient phenomenon confined to the most isolated of microscopic systems. This realization doesn't necessarily invalidate the Copenhagen or many worlds interpretations, but it fundamentally changes the conversation. It provides the physical backbone that Copenhagen lacked, explaining how the classical world emerges. And for many worlds, it explains the mechanism of branching. Decoherence describes how the different branches of the wave function lose contact with one another, creating the illusion of a single, unique history for every observer within their own branch. The deep question that remains is not about the mechanism, but about the nature of reality itself. Is the fog of decoherence merely hiding a vast, branching multiverse, or does it complete the process, leaving us with just one world? This final piece of the puzzle, the quantum to classical transition, is what makes decoherence so much more than a theoretical curiosity. It is the very reason our world feels solid and reliable. We live in a classical reality, a world of definite objects with clear properties. A coffee mug sits on a desk, a planet orbits a star. We never worry that our car might be in a superposition of being in the garage and on the freeway. Decoherence provides the elegant and continuous physical process that builds this familiar world directly from the strange quantum foundation beneath it. It's the mechanism that turns the potential of the quantum realm into the actuality of our everyday experience. The sheer scale of this process is what guarantees the classical world's stability. Consider any ordinary object around you, like the device you're using to watch this video. It is composed of an almost unimaginable number of atoms, octillions of them. Each one of those atoms is, in principle, a quantum system capable of existing in a superposition, but they are not isolated. they are bound together, vibrating with thermal energy, and constantly bombarded by photons from the lights in the room and molecules from the air. This creates a storm of environmental interaction so intense and so complex that any fragile quantum coherence between different states of the entire object is shattered in a time span too short to measure. For a macroscopic object, decoherence doesn't just happen quickly, it happens effectively instantaneously. The time it takes for a superposition of a baseball being in two places to be eradicated by the environment is many, many orders of magnitude shorter than the blink of an eye. This is why we never see such superpositions. They are not impossible, they are just unbelievably ephemeral, flickering out of existence before any conscious observation could ever hope to catch them. This leads to a profound shift in perspective. We don't live in a classical world because the quantum rules break down for large objects. Instead, we live in a world that appears classical because large objects are exceptionally bad at keeping quantum secrets. Their size and complexity make them incredibly leaky, constantly broadcasting their state to the universe. A single electron can maintain its quantum coherence for a relatively long time if carefully shielded in a vacuum and chilled to near absolute zero. But an object made of many particles cannot hide from the environment. The information about its position, for example, is continuously recorded in the paths of the photons that scatter off it and the air molecules that bounce against it. This process of environmental monitoring is so efficient that it selects for the most stable, robust states, the pointer states we discussed earlier. For objects we can see and touch, the most stable state is a well-defined position in space. Decoherence therefore explains not only why superpositions disappear, but also why the property of position is so fundamental to our classical reality. It's the property that survives the environmental onslaught. We can think of the universe as having a kind of resolution, much like a digital camera. At the finest scale, reality is pixelated into individual quantum events, full of fuzzy probabilities and potentialities. But when we zoom out to look at the big picture, the world of trees and buildings and people, this fine-grained quantum detail becomes blurred. Decoherence is the physical process that performs this blurring. It doesn't erase the underlying quantum pixels. It simply makes them impossible to discern from our coarse-grained, macroscopic perspective. The result is the smooth, definite, and predictable world we navigate every day. The transition from quantum to classical isn't a sudden leap across a mysterious boundary. It's a smooth, continuous fading of quantum effects as the number of particles in a system increases and its interactions with the environment multiply. Our classical reality is, in essence, the emergent result of quantum physics operating en masse in a noisy world. It is the most stable and predictable pattern that arises from the ceaseless quantum chaos happening at the microscopic level, a pattern so consistent that we can build entire civilizations upon its reliable rules. For decades, decoherence remained a powerful but largely theoretical idea. An elegant explanation that many believed must be true, but one that existed just beyond the reach of direct observation. How do you prove that a superposition is being destroyed by random environmental noise? The challenge was monumental, requiring technology sophisticated enough to isolate a quantum system, control its interactions with the environment with incredible precision, and then actually watch as coherence fades away. The turning point came at the dawn of the 21st century, when experimental physics finally caught up with theory, allowing us to witness decoherence in action. One of the most stunning demonstrations came from the University of Vienna, involving not a single atom or electron, but a molecule composed of 60 carbon atoms arranged in a hollow sphere, a buckeball or C60. This is an object large enough to be seen with powerful microscopes, a complex structure of hundreds of protons and neutrons. The team, led by Anton Zeilinger, performed a version of the classic double-slit experiment, the very experiment that first revealed the wave-particle duality of quantum mechanics. In the standard version, a beam of particles like electrons is fired at a barrier with two narrow slits. Even when the particles are sent one at a time, an interference pattern of light and dark bands builds up on a detector screen behind the barrier, proving that each individual particle behaves like a wave, passing through both slits simultaneously and interfering with itself. Zeilinger's team did this with C60 molecules. They heated a sample of these molecules and sent them one by one through a sophisticated interferometer, a device that uses a series of gratings to create the same essential condition as the double slits. Astonishingly, they observed a clear interference pattern. For the first time, it was demonstrated that an object comprised of 60 carbon atoms, a veritable giant in the quantum world, could exist in a superposition, traveling not just one path, but multiple paths through the apparatus at the same time. This was a revolutionary result in itself, but the true proof for decoherence came when they subtly altered the experiment. They introduced a controlled amount of a background gas into the chamber. These gas molecules acted as a miniature, tunable environment. As the density of the gas increased, creating more opportunities for the buckaballs to randomly collide, the beautiful interference pattern began to fade. The sharp bands of light and dark gradually smeared out, eventually disappearing entirely. They were watching in real time as the environment measured the molecules. Each collision with a gas molecule effectively recorded which path the buckaball had taken, destroying the delicate phase relationship necessary for interference. They had not just inferred decoherence, they had made it visible. Around the same time, in laboratories focused on quantum computing, another powerful line of evidence was emerging. Quantum computers rely on quantum bits or qubits, which are tiny circuits or trapped ions that must maintain their superposition states to perform calculations. The greatest enemy of a quantum computer is decoherence. It is the noise that destroys the fragile quantum information. Researchers working with superconducting qubits, which are tiny loops of wire cooled to near absolute zero, developed an incredible ability to control their environment with exquisite precision. They can literally play the role of the environment themselves. By carefully applying tailored electromagnetic pulses, they can simulate the effect of a noisy environment on a single qubit. They can start with a qubit in a perfect, clean superposition and then gradually turn up the dial on this artificial noise. Using sophisticated measuring tools, they can track the qubit's quantum state as it evolves. What they see is a direct visualization of decoherence. The clear, wavy signature of a quantum superposition gradually blurs and simplifies into the dull signature of a classical probability mixture. The quantum information leaks out into the simulated environment exactly as the theory predicts. These experiments are not just observations. They are full-blown choreographies of the decoherence process, allowing scientists to study its timescales and mechanisms in incredible detail. The evidence doesn't stop there. Experiments with trapped ions, single atoms held perfectly still by electric and magnetic fields in an ultra-high vacuum, provide perhaps the most pristine view of the process. By using lasers to cool the ions to a virtual standstill and shielding them from all external fields, scientists can create a nearly perfect quantum system. They can then coax a single ion into a superposition of two different energy states. In this perfect isolation, the ion can maintain its coherence for a remarkably long time. But then, by allowing a few photons from a carefully controlled light source to interact with the ion, they can introduce a minimal environmental interaction. They can watch as the coherence time, the lifespan of the superposition, plummets in direct proportion to the number of photons they allow to measure the system. This is decoherence stripped down to its most fundamental level, a single quantum system and a handful of environmental particles. The correlation is perfect and undeniable. The dream of a perfectly isolated quantum system is just that, a dream. Any connection to the outside world, no matter how small, inevitably seeds the process that leads to the classical reality we know. These experiments collectively form an overwhelming case. They transform decoherence from a compelling hypothesis into a well-established fact of nature. We have moved from philosophical speculation to hard, empirical data. We can now control decoherence, measure its rate, and even engineer systems to fight against it, as quantum computer scientists do every day. This body of work provides the crucial physical evidence that was missing for so long, solidifying decoherence's role as the fundamental bridge between the quantum and classical worlds. It confirms that the definite world we experience is not a separate realm governed by different laws, but a direct and inevitable consequence of quantum physics playing out in an open, interactive universe. The fog is real, and we have learned not only to see it but to understand its source. With the mechanism of decoherence now firmly established, we can return to one of the most ambitious interpretations of quantum mechanics and see it in a completely new light. The many worlds interpretation, which once seemed like a philosophical thought experiment, finds in decoherence the precise physical process it was missing. Decoherence provides the missing link, transforming the abstract mathematics of endless branching into a concrete description of how a single universe gives rise to the appearance of multiple distinct realities. Recall that the central challenge for many worlds was explaining how we, as observers, experience only one outcome from a quantum event. If the wave function never collapses and all possibilities are realized, why are we unaware of the other branches? Decoherence supplies the elegant answer. It doesn't just make superpositions unobservable, it actively and continuously creates the conditions for separate worlds to emerge. The process of environmental entanglement is what physically severs the connections between branches. Think of the universe's wave function not as a single thread, but as a vast, intricately woven tapestry. Decoherence is the force that frays this tapestry along its seams, pulling the threads apart into individual, non-interacting strands. Each strand represents a branch, a world where a specific set of quantum possibilities has been actualized through its interaction with the environment. In the case of Schrödinger's cat, decoherence doesn't just make the alive-dead superposition impractical to detect. It actively correlates the alive outcome with one vast specific state of the environment and the dead outcome with another. These two environmental states become so different, so orthogonal, that they can no longer influence one another. They become parallel storylines in the history of the cosmos. This resolves the most significant practical objection to many worlds. If other branches are real, why can't we see any evidence of them? The reason is that decoherence doesn't merely hide these branches, it makes them fundamentally inaccessible. For an observer in the branch where the cat is alive, the branch where the cat is dead is not just far away, it is completely disconnected from their experiential reality. The information that defines the dead cat branch is encoded in a different set of environmental degrees of freedom. The paths of air molecules, the patterns of scattered light that are forever out of reach. It would be like trying to hear a whisper in a specific room in a specific house on a different continent without any communication link. The branches lose their quantum coherence with one another, meaning they can no longer interfere. This loss of interference is what allows each branch to evolve independently, following its own unique, classical-looking timeline. From within any single branch, the universe behaves exactly as if it were the only one, precisely because all the other branches have been decoupled from it by the relentless process of decoherence. In this synthesized view, the act of branching is not a sudden, discrete event. It is a continuous, smooth process driven by decoherence. Every time a quantum system becomes entangled with its environment, the number of distinct, independent branches increases. Most of these branches are microscopically differing only in the spin direction of a single electron that no one observed. But when a quantum event becomes amplified, as in the Geiger counter connected to the poison vial, that microscopic difference quickly escalates into a macroscopic divergence. The branching of the universe is happening constantly at an unimaginable rate, but we are only aware of the single, consistent history of the branch we inhabit. Decoherence provides the dynamic mechanism that takes the universal wave function and continuously differentiates it into the myriad of parallel worlds that the many worlds interpretation proposes. It answers the how with a tangible physical process, grounding a once speculative idea in the firm foundation of environmental interaction. While decoherence provides a powerful explanation for why the quantum world appears classical from our limited viewpoint, it leaves a fundamental philosophical question wide open. If all the branches of the wave function continue to exist, just permanently separated from one another, then what is the actual nature of reality? Is it a vast, ever-branching multiverse where every possibility is realized? For some physicists, this conclusion is a bridge too far. They seek a theory that not only explains our experience but also restores a single, objective reality. This has led to a fascinating class of ideas known as objective collapse theories, which propose that wave function collapse isn't an illusion created by environmental noise, but a real, physical event that happens spontaneously in nature. The most developed of these models is the Gerardi-Rimini-Weber or GRW theory. Its core premise is elegant in its simplicity. What if microscopic particles have a tiny but non-zero probability of spontaneously collapsing out of their superposition at any given moment? The GRW model posits that every particle in the universe has an incredibly small chance, perhaps once every 100 million years or so, to undergo a spontaneous localization. In this event, the particle's wave function, which might be spread out over a region of space, suddenly and randomly snaps into a specific, well-defined location. For a single particle, this event is so rare as to be almost negligible. But here's the crucial amplification mechanism. In any object made of many particles like a cat or a measuring device, the particles are all entangled. The theory proposes that if one particle in the system collapses, it instantly drags the entire entangled system with it into a definite state. For a macroscopic object containing trillions upon trillions of particles, the probability that at least one of them will undergo collapse in even a minuscule fraction of a second becomes effectively 100%. This is why large objects are always found in definite states. They are constantly being hit by these random, spontaneous collapses. In this view, when we open Schrödinger's box, we aren't discovering a pre-existing state or branching into a new universe. We are simply witnessing the result of the latest in a continuous storm of mini-collapses that have already definitively determined the cat's fate. A different, yet equally profound, approach comes from renowned physicist Roger Penrose. He suggests that the trigger for collapse may not be random, but rooted in one of the most fundamental forces in the universe, gravity. Penrose's conjecture is that a superposition becomes unstable because of its own gravitational field. Imagine an object in a superposition of two different locations. In one branch, its mass is creating a gravitational pull in one place. In the other branch, the same mass is pulling from a different location. According to general relativity, mass warps spacetime. Penrose argues that having a single object in two places at once would correspond to spacetime being warped in two conflicting ways simultaneously. He proposes that this situation, a superposition of different spacetime geometries, is inherently unstable. The universe, in a sense, cannot make up its mind about how to curve space-time around the object. This instability would cause the superposition to decay or collapse into one definite location after a very short time. The larger the object, the greater its mass, and the more severe this spacetime conflict becomes, leading to a faster collapse. For a single electron, the collapse time would be astronomically long. But for a speck of dust, let alone a cat, the collapse would be instantaneous. In this elegant hypothesis, the transition from quantum to classical is dictated by the scale at which gravity becomes significant, weaving together the two great yet seemingly incompatible pillars of modern physics, quantum mechanics and general relativity. The distinction between these objective collapse models and the many worlds view, supplemented by decoherence, is profound and hinges on the nature of reality itself. In the many worlds picture, reinforced by decoherence, reality is a multiverse of relative states. There is no single privileged outcome. What you perceive as the outcome is simply the branch you happen to be on, and the collapse is an illusion born of your loss of access to the other branches. It is a theory about perspectives within a whole. Objective collapse theories, by contrast, aim to restore an absolute, observer-independent reality. They assert that only one thing actually happens. The wave function doesn't just appear to collapse from our point of view. It physically and objectively does collapse, singling out one history as the one true history of the universe. The other possibilities are not just inaccessible, they are erased from existence. This fundamental difference makes the theories, in principle, testable. While current technology makes it extraordinarily difficult, the spontaneous collapse postulated by GRW, or the gravity-induced collapse suggested by Penrose, would produce subtle but potentially detectable effects. For instance, a particle undergoing spontaneous collapse would very slightly increase its energy, which could manifest as a faint background noise. Experiments are being designed to push the limits of isolating quantum systems to see if there is a fundamental limit to how long coherence can be maintained, a limit that might be imposed not by practical engineering challenges but by a fundamental new law of nature. Finding such a limit would be a monumental discovery, pointing toward an objective collapse mechanism and potentially ruling out the pure, infinite branching of many worlds. Until such decisive evidence is found, we are left with a captivating choice between two radically different visions of cosmos, one that is unfathomably vast and endlessly branching, and another that is singular and definite, with collapse woven into the very fabric of spacetime. So we've seen how decoherence acts as a relentless editor, silencing the quantum whispers of superposition by entangling them with the noisy environment. But this powerful mechanism gives rise to an even deeper question. Why, out of all the countless properties a quantum system could possess, do we consistently agree on a select few? Why is it that when you and I look at a chair in a room, we both see it in the exact same location? We don't argue about its color or its shape because that information is also reliably present. But the most fundamental point of agreement is always its position. This universal consensus suggests that some information about the world is not just recorded by the environment, but is broadcast by it, copied over and over again until it becomes an undeniable public fact. This is the brilliant insight of quantum Darwinism, a theory that proposes our classical reality isn't just a random outcome of environmental noise, but is actively selected for its ability to be copied and shared. The core idea of quantum Darwinism is as elegant as it is powerful. It posits that the states we perceive as classical, the so-called pointer states we discussed earlier, are not chosen arbitrarily. They are the ones that are most fit to survive the process of decoherence. But fitness here has a very specific meaning. It is the ability of information about that state to be redundantly imprinted onto the environment. Think of it like a news story breaking in a major city. The event itself is the quantum system, but for it to become a widely accepted fact, it can't just be reported by one journalist. It needs to be picked up by dozens of news outlets, television stations, and social media feeds. Each of these outlets creates a separate, independent record of the event. The more redundant copies that exist, the more objective and real the event becomes to the public. In exactly the same way, a quantum system's pointer state becomes classical when information about it is copied not just once, but thousands or millions of times into the environment. Let's take that chair as our example. The chair is a complex quantum system, but its quantum aspects are instantly decohered by the environment. Now consider what that environment is doing. Every photon of light that bounces off the chair carries away a tiny piece of information, primarily about where the chair is located. These photons scatter in all directions. Some hit the walls, some hit your eyes, and others might travel out the window. Similarly, the air molecules constantly jostling against the chair also record its position. Each collision is a minute measurement. Crucially, these environmental records are largely independent of one another. The photon that reaches your eye carries the same essential message, the chair is here, as the photon that reaches my eye or the air molecule that bounced off its leg. The information about the chair's exact quantum energy state or the spin of its individual atoms is far too fragile and specific to be copied in this robust, redundant way. It gets lost in the noise, but the information about its location is so stable and so easily recorded that it gets broadcast far and wide. This process creates what physicists call a fossil record in the environment. Just as paleontologists can piece together the history of life by examining multiple redundant fossils found in different rock layers, any observer can come along and determine the state of the chair by intercepting just a tiny, random fraction of these environmental messengers. You don't need to examine all the scattered photons, you only need to catch a handful to be completely confident of the chair's position. I can do the same completely independently. Because we are both sampling from the same vast, redundant reservoir of information, we will inevitably arrive at the same conclusion. This is the origin of objectivity. It's not that there is one single, mystical reality that we both magically perceive. It's that the state of the system has left so many identical traces in the world that our individual measurements are guaranteed to agree. The environment itself acts as a universal communication channel, ensuring consensus. Quantum Darwinism, then, provides a stunningly complete answer to the question of why we see the world we do. It's not enough for a state to simply be stable against decoherence. It must also be highly copyable. The pointer states that win the evolutionary competition are the ones that can spawn the most offspring in the form of information-bearing fragments in the environment. Position is the champion of this competition. It is exceptionally easy for the environment to record and replicate information about where something is. This explains the overwhelming primacy of position in our classical experience. We live in a world of objects in definite locations because information about location is the most efficiently and redundantly disseminated information of all. This theory beautifully completes the picture painted by Decoherence, showing that our objective, agreed-upon reality is not a given, but an emergent property of a Darwinian selection process where the fittest information survives by being copied until it becomes a public fact. This journey into the quantum foundations of reality inevitably leads us to one of the most personal and profound questions of all. What does it mean for our own lives? If our choices are ultimately just the outcome of quantum processes playing out in our brains, then what becomes of our cherished notion of free will? The interpretation we adopt paints strikingly different pictures of human agency, forcing us to confront whether our decisions are an illusion, a roll of the dice, or something else entirely. Consider the implications of the many worlds interpretation combined with decoherence. In this view, the universe's wave function evolves in a perfectly deterministic and unitary way according to the Schrödinger equation. There are no random collapses. Every single quantum possibility is realized in some branch. This means that at this very moment, a version of you is deciding to continue watching this video while another version has already clicked away. A version is reaching for a snack while another remains focused. Every conceivable choice, no matter how minor, is made somewhere in the multiverse. From a God's eye view, the entire history of the cosmos is a single, vast, and predetermined mathematical structure. there is no randomness, only the inevitable unfolding of every possible timeline. So, where does that leave your feeling of making a choice? It suggests that your sense of deliberation is real, but the outcome was always guaranteed within the branch you inhabit. Your free will in this picture is the experience of navigating a single, predetermined path through an infinite labyrinth of possibilities. You have the freedom to do what you are always going to do in this specific world, but you lack the ultimate freedom to have done otherwise in any absolute sense, because a version of you did do otherwise in a parallel branch. This is a deeply challenging notion that seems to reduce our lives to a complex, predetermined script. Now, contrast this with the perspective offered by objective collapse theories, like the GRW model or Penrose's gravity-induced collapse. These theories reintroduce genuine, fundamental randomness into the heart of physics. The moment of wave function collapse is not determined by prior states. It is a truly stochastic or random event. In this universe, the future is not written. When you face a decision, the quantum events in your brain that correspond to weighing options could literally collapse one way or the other based on no prior cause. This injects an element of chance into the chain of cause and effect. In this view, free will might be seen as our conscious mind's ability to influence or capitalize on these random quantum events. Perhaps our deliberation process biases the probabilities, making one outcome more likely than another, but the final click into a definite thought still contains an irreducible element of randomness. This doesn't necessarily feel like a satisfying form of free will either. It exchanges a deterministic prison for a casino, where our choices are ultimately the result of cosmic dice rolls. Is a decision that hinges on a random quantum fluctuation any more free than one that was predetermined? This leads us into the ancient philosophical debate between determinism and libertarian free will. Hard determinism argues that if the universe is governed by strict cause and effect, whether classical or quantum in the many-world sense, then free will is an illusion. Our brains are physical systems, and their states are the consequences of prior states, all the way back to the Big Bang. We feel like we are choosing, but we are simply witnessing the inexorable execution of a cosmic program. Compatibilism offers a middle ground, suggesting that free will can be redefined to be compatible with determinism. It argues that free will isn't about being able to break the chain of causality, but about acting in accordance with our own desires, beliefs, and reasoning without external coercion. In this view, you are exercising free will when you choose a salad over a burger because you want to be healthy, even if that desire was itself caused by prior events. This perspective can be adapted to fit within the many worlds framework. Your actions are determined by who you are in your branch, and that you is a product of a consistent history. The introduction of true randomness from collapse theories doesn't automatically rescue libertarian free will, which demands that we are the ultimate, uncaused originators of our actions. Randomness seems to be the opposite of control. If my decision to write a sentence is the result of a quantum fluctuation, it's hard to see how that constitutes a meaningful act of my will. It appears to remove agency rather than grant it. Some philosophers and scientists like Roger Penrose and neuroscientist John Eccles have speculated that consciousness might somehow harness or influence these quantum collapses, but such ideas remain highly speculative and lack a clear mechanism. The uncomfortable truth may be that our intuitive sense of being an uncaused cause, a purely self-determining agent, might not find a comfortable home in any of our current physical descriptions of the universe, whether they are deterministic or probabilistic. Ultimately, the question of free will in the quantum era remains wide open. The physics gives us the boundary conditions, but the interpretation is still a matter of deep personal and philosophical reflection. Does the infinite branching of the multiverse make your life's path feel more or less significant? Does the idea of random collapses make your choices feel more authentic or merely arbitrary? There are no easy answers, but the very fact that we can ask these questions highlights a remarkable thing. Our universe or multiverse has produced creatures complex enough to look back at their own constituent parts and wonder how they fit into the grand scheme of things. The search for free will is, in itself, one of the most compelling expressions of our conscious experience. This brings us to a pivotal and deeply philosophical crossroads in our journey, forcing us to re-evaluate one of the most tantalizing ideas from the early days of quantum theory: the special role of the conscious observer. The Copenhagen interpretation, while often misinterpreted, certainly placed the act of measurement on a pedestal, and it was all too easy to slip from the idea of a classical measuring device to the notion that a conscious mind was the ultimate arbiter of reality. It suggested a universe that remained in a state of fuzzy potential until a conscious being looked at it, thereby solidifying existence itself. This idea is both powerful and profoundly unsettling, as it seems to place human consciousness at the very center of the cosmic drama. But Decoherence challenges this anthropocentric view in the most direct way possible, arguing that the job of collapsing possibilities is handled tirelessly and automatically by the mundane physical world all around us. The environment in the Decoherence framework is the ultimate unconscious observer. It is a relentless, mindless recording device. Every photon, every air molecule, every vibration that interacts with a quantum system is performing a miniature measurement, extracting a tiny bit of information and carrying it away. This process requires no awareness, no sophisticated laboratory equipment, and certainly no human presence. It happens in deep space where no life exists, inside stars where matter is torn apart, and in the darkest, coldest voids between galaxies. The transition from quantum possibility to classical definiteness occurs constantly, driven by these blind, physical interactions. From this perspective, the solidity of the moon when no one is looking is guaranteed not by some vague potential for a future observation, but by its continuous and vigorous interaction with sunlight, solar wind, and the cosmic microwave background. The environment is always looking, and in doing so, it ensures that macroscopic reality exists independently of us. Decoherence, therefore, effectively displaces consciousness from its privileged position in physics. It severs the mysterious link between mind and matter that the measurement problems seem to suggest, restoring a world that is objective and real in its own right, long before any conscious being evolves to perceive it. Yet, even as Decoherence resolves the practical problem of how definite states emerge, it leaves a much deeper and more intractable puzzle entirely untouched. This is the so-called hard problem of consciousness. Decoherence explains how a system appears to be in a single state to an observer. It explains the objectivity of the measurement outcome. But it does not and cannot explain the subjective experience of that outcome, what it is like to be that observer. This is the monumental gap between the third-person description of brain processes and the first-person reality of feeling, thought, and awareness. We can fully describe, in principle, how photons entering your eye trigger a cascade of neural events that decohere into a specific brain state corresponding to seeing a red apple. But this entire physical account says nothing about why this physical process should be accompanied by the private, qualitative experience of the color red, the redness itself. Why isn't all of this information processing happening in the dark without any inner light? This distinction highlights the two very different roles an observer can play. In the decoherence picture, an observer is simply a complex physical system that becomes correlated with its surroundings. Your body and brain are parts of the environment, subject to the same relentless decoherence as everything else. In this objective sense, you are an observer because you reliably record information. But this is a far cry from the other meaning of observer, a conscious self, a locus of subjective experience. Decoherence brilliantly explains how the book of reality gets written in a single, consistent script that all observers can agree upon. but it has nothing to say about how or why there is someone inside your head reading the book. The what it is like of experience remains a complete mystery. Some thinkers, like mathematical physicist Roger Penrose, argue that this gap is not a minor detail but a glaring clue that our current physics is incomplete. He suspects that a proper theory of quantum gravity, which would unite the theories of the very large and the very small, might also need to account for the phenomenon of consciousness. In his view, the non-algorithmic, holistic nature of subjective experience might find its roots in an as-yet unknown quantum process within the brain. This remains a highly speculative minority view, but it underscores the fact that explaining the objective world is one thing, and explaining the existence of subjective perspectives on that world is another challenge entirely. Therefore, while decoherence successfully evicts consciousness from its role as the cause of wavefunction collapse, it does not eliminate the profound mystery of consciousness itself. We are left with a universe that is robustly real and independent of our minds, thanks to the ceaseless measurements of the environment. Yet, within that universe, we find ourselves as beings who not only record information but also experience it. The easy problems, how we discriminate stimuli, how we focus attention, how we report on our mental states, may one day be explained by cognitive neuroscience and decoherence-like processes in the brain. But the hard problem, why there is any experience at all, stands as a monument to the limits of our current physical understanding. Decoherence gives us a world that is there when we aren't looking, but it doesn't tell us why there is anyone to look in the first place or what it means to see. This relentless and universal process of decoherence is not merely a fascinating feature of our universe. It is also the single greatest challenge standing between us and one of the most transformative technologies ever conceived, the quantum computer. To understand why, we need to grasp the fundamental difference between a classical computer bit and a quantum bit or qubit. A classical bit is a simple switch. It can be either a 0 or a 1, a state that is incredibly robust and easy to maintain. You can store a 1 on a hard drive for decades and it will remain a 1, unaffected by the gentle warmth of a room or the faint whisper of background radiation. A qubit, however, is a creature of a far more delicate nature. It harnesses the power of superposition, meaning it can be a 0, a 1, or any complex combination of both simultaneously. This is the source of a quantum computer's potential for immense speed-up on certain problems, allowing it to explore many computational paths at once. But this superpower comes at a terrible cost: extreme fragility. The very quantum coherence that gives the qubit its power is exquisitely sensitive, and it is constantly under attack from the very same environmental interactions that make our classical world seem solid. Decoherence is in essence the kryptonite of quantum computing. It is the process that causes a qubit to lose its precious quantum information. Imagine a qubit carefully prepared in a perfect, clean superposition. A balanced state of both 0 and 1, ready to perform a calculation. But the qubit is not floating in a perfect void. It is built on a physical substrate, a chip that has its own atomic vibrations, which we perceive as heat. It is surrounded by the faintest traces of gas molecules and is constantly bathed in stray electromagnetic fields. Even the cosmic rays passing through the laboratory walls can be enough to cause a disruption. Each of these environmental factors acts as a tiny, unwanted measurement. A single photon bouncing off the qubit can become entangled with it, carrying away a piece of information about its state. This intrusion destroys the delicate phase relationships that define the superposition. The qubit doesn't just randomly flip from a 0 to a 1. Its quantum state decays into an ordinary classical probability. The coherent superposition, which was like a perfectly tuned chord of two notes playing at once, collapses into a dull, single tone. The qubit becomes just a probabilistic bit, and all the quantum parallelism that made it special is lost. This event is called a decoherence event, and the average time a qubit can maintain its coherence before such an event occurs is known, quite ominously, as its lifetime. The entire field of quantum computing is therefore a monumental battle against this inevitable decay. The first and most crucial line of defense is to build a fortress of isolation around the qubits. This is why quantum computers are housed in some of the most extreme artificial environments on Earth. The most common type of quantum processor, the superconducting qubit, is a tiny loop of metal that must be cooled to temperatures within a few thousandths of a degree above absolute zero. These temperatures are colder than the vacuum of deep space. This incredible chill is necessary to freeze out the thermal vibrations of the qubit's own atoms, which are a primary source of decoherence. The entire processor is suspended inside a massive, intricate refrigerator, shielded from external magnetic fields by layers of specialized metal, and operated in an ultra-high vacuum to eliminate collisions with air molecules. Engineers are, in effect, trying to create a pocket of the universe where environmental interactions are brought to a near standstill, giving the qubits a fighting chance to maintain their quantum states long enough to be useful. But perfect isolation is an impossible dream. There will always be some residual noise that seeps through the defenses. This is where a second, brilliantly clever strategy comes into play, known as dynamical decoupling. Think of a qubit as a spinning top. If you leave it on a wobbly table, it will quickly fall over. But if you gently tap the table at just the right rhythm, you can actually stabilize the top, counteracting the wobbles and keeping it upright. Dynamical decoupling applies this same principle to a qubit. By hitting the qubit with a carefully timed sequence of precise microwave pulses, scientists can effectively refocus it. These pulses flip the qubit's state in such a way that the slow, cumulative effects of the environmental noise are cancelled out. It's a dynamic shielding technique that doesn't try to eliminate the noise, but instead manipulates the qubit itself to make it deaf to the environmental chatter for short periods. This can extend the qubit's coherence time significantly, but it requires exquisite control and adds complexity to an already challenging task. Despite these heroic efforts, the coherence times of individual qubits are still far too short for meaningful computation. The errors introduced by decoherence are inevitable. This realization has led to the most powerful and ambitious strategy of all, quantum error correction. Instead of trying to build a perfect, noise-free qubit, a goal that may be physically impossible, quantum error correction accepts that decoherence will happen and builds a system that can detect and correct the errors in real time. The core idea is to store the information of a single, fragile, logical qubit across multiple, imperfect physical qubits. By entangling these physical qubits in a specific way, the system can continuously monitor them. If one physical qubit suffers a decoherence event and flips its state, the entanglement within the group will be disrupted, creating a detectable signature without destroying the underlying information of the logical qubit. A correction signal can then be applied to fix the error before it corrupts the calculation. This is analogous to the way classical computers use redundancy, like storing a bit of information 3 times and taking a majority vote to correct an error. But quantum error correction is vastly more complex because you cannot simply copy a quantum state, a rule known as the no-cloning theorem. Instead, the information is spread out non-locally through entanglement. The truly remarkable promise of quantum error correction is that if you can get the error rate per physical qubit below a certain threshold, and you have enough physical qubits to encode each logical one, you can theoretically extend the coherence time of the logical qubit indefinitely. It creates a virtuous cycle where adding more imperfect qubits and implementing the correction code leads to a more stable and reliable quantum computer overall. We are currently in the noisy intermediate scale quantum, or NISQ era, where we have processors with dozens or even hundreds of qubits, but not yet enough to implement full-scale error correction. The race is on to increase the number and quality of qubits to cross that critical threshold. an achievement that would mark the beginning of truly fault-tolerant quantum computation and unlock the technology's full potential. Imagine a future where the fragility of quantum states is no longer a barrier, but a challenge we have mastered. The battle against decoherence, which today confines quantum computers to cryogenic freezers, could be won not just by better isolation, but by revolutionary technologies that actively tame environmental noise. This future relies on two powerful approaches: building quantum systems that are inherently robust against decoherence, and creating architectures that can fight it off in real time. The first path leads us to a remarkable class of particles that don't exist in the three dimensions we're familiar with, but in a more abstract mathematical space. These are anyons, and the qubits built from them, known as topological qubits, represent a potential paradigm shift. Unlike today's superconducting qubits, where information is stored in a fragile property like the charge or flux of a tiny circuit, a topological qubit encodes information in the global topological properties of a system. Think of it like this: you can tie a simple knot in a shoelace. You can jiggle the lace, stretch it, or twist it, but the fundamental property of having a knot, its knottedness, remains unchanged. Similarly, the information in a topological qubit is not stored in a specific location that can be easily disturbed by a stray photon. It is woven into the braided world lines of anyons. A local environmental perturbation, like a random collision, might jostle the system, but it cannot easily alter this global topological property. It would be like trying to untie a knot by poking just one point on the shoelace. The information is protected by its non-local nature. This inherent resilience could lead to qubits with coherence times that are not milliseconds, but potentially hours or even longer, dramatically reducing the overhead needed for error correction and bringing us much closer to practical, fault-tolerant quantum computers. While topological qubits offer a passive, built-in defense, another futuristic strategy involves an active, relentless counterattack against decoherence. This is the realm of advanced quantum error correction, or QEC, scaled to a level we can only dream of today. In this vision, a quantum computer would not be a simple collection of qubits, but a sophisticated, layered ecosystem. Each precious logical qubit, which holds the actual computational information, would be comprised of hundreds or even thousands of interconnected physical qubits. These physical qubits would act as a protective shield, continuously performing diagnostic checks on each other. Sophisticated control systems would run complex algorithms in real time, using the entanglement between these helper qubits to detect the faintest whisper of decoherence the moment it begins to affect one part of the system. The system wouldn't wait for an error to happen. It would sense the instability that precedes it. Then, in a flash, it would apply a precisely calibrated counterpulse of energy to correct the deviation, all without ever directly measuring and thereby collapsing the logical qubit it is protecting. This would be like having a team of microscopic guardians constantly monitoring the structural integrity of a building, automatically applying counterpressure to any beam that starts to bend, ensuring the entire structure remains perfectly sound through any storm. This level of active stabilization would effectively create a quiet, synthetic environment for the logical qubit, an artificial pocket of reality where decoherence is continuously neutralized, allowing complex calculations to proceed for lengths of time that are currently unimaginable. The ultimate goal would be to merge these approaches, creating hybrid systems that combine the inherent stability of topological protection with the dynamic responsiveness of advanced error correction. Picture a quantum processor where the basic building blocks are robust topological qubits, each already resistant to most common sources of noise. These stable qubits are then networked together into a larger error-correcting code, providing a second layer of defense against any rare, large-scale disturbances that might threaten the entire processor. This multi-layered defense would create a quantum computing platform of unprecedented reliability. the implications for fields like materials science, drug discovery, and climate modeling would be profound. We could simulate the behavior of new molecules with perfect accuracy, designing life-saving drugs or revolutionary new materials without costly and time-consuming lab trials. We could model the incredibly complex interplay of factors driving climate change with a fidelity that allows for truly predictive and effective solutions. Mastering decoherence wouldn't just be about building faster computers. It would be about granting ourselves a new lens through which to understand and manipulate the fundamental rules of our universe, transforming our capacity to solve some of humanity's most enduring challenges. But what does this hard-won mastery over the quantum world actually unlock for us in our daily lives? Let's step away from the massive, supercooled laboratories and into a future where the fruits of this battle are as personal and accessible as the smartphone in your pocket. Imagine a world where the incredible sensitivity of the quantum realm is no longer locked away in a vacuum chamber, but is instead integrated into the very fabric of our everyday technology. This is the promise of personal quantum devices, a future built directly upon our ability to control decoherence, bringing the power of superposition and entanglement out into the open air. The first and most immediate revolution will likely come in the form of quantum sensing. Think about the GPS on your phone. It works by triangulating signals from satellites orbiting thousands of miles above the Earth. It's incredibly useful, but it's also fragile. It fails inside buildings, in dense urban canyons, and underground. Now, imagine a navigation device that doesn't rely on any external signals at all. Instead, it uses a miniature, exquisitely shielded quantum accelerometer and gyroscope. This sensor wouldn't measure your movement relative to satellites, but would sense infinitesimally small changes in the local gravitational field and rotations of the Earth itself. By maintaining a cloud of atoms in a coherent superposition, this sensor could detect changes in acceleration so tiny they were previously immeasurable outside a lab. The result, perfect centimeter-scale precision navigation that works anywhere on the planet, deep in a mine, at the bottom of the ocean, or in the labyrinthine corridors of a giant subway system. You would never be lost again because your device would always know its exact position relative to the Earth's own gravitational fingerprint, completely independent of satellites. The impact on healthcare could be even more profound. Today, getting a detailed diagnostic scan means traveling to a hospital and lying inside a massive multi-ton machine like an MRI. These machines are powerful because they can detect the subtle magnetic signals from the atoms in your body. But what if that same principle could be scaled down? With decoherence under control, we could develop handheld quantum magnetometers of unimaginable sensitivity. A doctor in a remote village could wave a scanner over a patient and not just see the structure of an organ, but detect the faint magnetic fields generated by the electrical activity of individual nerve clusters in the brain or the muscular tissue of a beating heart. This would allow for the early detection of neurological conditions like epilepsy or Parkinson's disease by identifying anomalous patterns of activity long before major symptoms appear. It could detect inflammation in the heart muscle after a minor infection that would be invisible to current technologies. This isn't just a better scan. It's a fundamental shift from diagnosing structural problems to diagnosing functional and electrical ones at their very inception, moving medicine from treatment to true proactive prevention. This quantum sensitivity would extend to our understanding of the world around us in ways that feel like science fiction. Consider a simple app on your personal device that could analyze the composition of anything you point it at. Using quantum-enhanced spectroscopy, the device could fire a harmless beam of light at a piece of fruit, and by analyzing the quantum states of the reflected photons with incredible precision, instantly determine its exact nutritional content, its level of ripeness, and even whether it contains traces of pesticides or allergens. You could test the authenticity of a gemstone or a valuable painting without damaging it. An engineer could scan a bridge or an airplane wing and detect microscopic stress fractures and metal fatigue long before they become visible to the naked eye or to conventional sensors, preventing catastrophes by sensing the whispers of impending failure. Environmental scientists could carry handheld units that detect specific pollutant molecules at parts per quadrillion concentrations in the air or water, mapping contamination with a resolution that is simply impossible today. The common thread enabling all these wonders is the ability to maintain quantum coherence in a small, portable, and rugged device. This is the real breakthrough. It won't happen by building a perfect vacuum or a miniature supercryostat into your phone. Instead, it will rely on the sophisticated error correction and dynamic decoupling techniques we discussed, all miniaturized onto a chip. The device will constantly fight a silent, high-speed battle against decoherence, using clever algorithms to correct for the thermal noise and vibrations of everyday life. It will create a stable, synthetic quantum environment on the go, a tiny island of quantum order within the classical chaos of the world. This transition from quantum technology as a massive infrastructure project to quantum technology as a personal tool will be as transformative as the shift from room-sized mainframe computers to the laptops and smartphones we use today. It will weave the uncanny precision of the quantum world into the tapestry of our daily decisions, empowering us with a clarity of perception that borders on the superhuman. Now, let's push this idea to its most extraordinary limit. We've seen how decoherence forces the macroscopic world to behave classically, but what if we could reverse that process? What if, instead of fighting a defensive battle against environmental noise, we could achieve such perfect control over a system's interactions that we could induce and sustain quantum behavior in objects large enough to see with the naked eye? This is the frontier of macroscopic quantum objects, a realm where the bizarre rules of the quantum world would no longer be confined to the lab but would become a tangible part of our engineered environment. The first and most startling possibility is the creation of materials that exist in a state of macroscopic quantum coherence. Imagine a new class of metamaterials engineered not just for their chemical composition but for their quantum mechanical architecture. These materials wouldn't be defined by being hard, soft, or elastic in the classical sense. Instead, their very identity would be a sustained superposition. A block of such a material might not have a single, definite crystalline structure. It could exist in a quantum blend of two different atomic lattices simultaneously. This wouldn't be a chaotic mixture, but a coherent superposition, meaning the material would exhibit properties that are a ghostly average of both potential structures. You could have a substance that is simultaneously as thermally conductive as diamond and as electrically insulating as rubber, its behavior shifting depending on how it is measured or used. The applications would be revolutionary. You could design a wing for an aircraft that dynamically optimizes its aerodynamic profile by existing in a superposition of shapes, perfectly adapting to turbulence in real time. Or you could create a building material that exists in a superposition of being rigid and flexible, allowing it to dissipate the energy of an earthquake by literally vibrating in multiple ways at once, absorbing shock waves that would shatter conventional concrete and steel. This leads to an even more visually spectacular phenomenon, quantum levitation. We already have a glimpse of this with superconductors, where magnetic flux is quantized and locked, allowing them to float above magnets. But true quantum levitation would be something else entirely. It would rely on an object being in a persistent, macroscopic superposition of position. Picture a sculpture hovering motionless in the center of a room, with no visible support, no magnetic fields, and no energy input. This isn't magic. It's the object existing in a coherent state where its own wave function is spread out in such a way that the probability of it being anywhere other than that precise point in space is zero. It would be levitating because it is, in a very real sense, everywhere and nowhere at once. its position stabilized by quantum interference effects on a grand scale. The engineering required to shield such an object from decoherence would be monumental, perhaps involving active quantum error correction fields that constantly negate any environmental interaction. But if achieved, it would create frictionless bearings for everything from transportation to energy generation, and redefine our very concept of solid matter. The implications for information processing would be equally profound. We are used to computers processing information in a linear, deterministic sequence. But a macroscopic quantum object could, in principle, process information in a massively parallel way across its entire structure. A single, coherent crystal could act as a natural quantum computer, where calculations are performed not by flipping bits, but by evolving the complex interference patterns within the object's wave function. Data storage would be transformed. Instead of saving a file as a series of zeros and ones on a disk, you could imprint information onto the quantum state of a macroscopic object, like encoding an entire library into the precise vibrational superposition of a small diamond. This information would be incredibly dense and, as long as coherence is maintained, immune to classical degradation. The very act of observing it incorrectly would destroy the data, making it the ultimate in secure, one-time read storage. Living in a world where macroscopic quantum effects are commonplace would fundamentally alter our intuitive understanding of reality. The clear, definite world we take for granted would be revealed as a special case, a low-energy equilibrium state. We would be surrounded by objects that visibly demonstrate the principles of superposition and entanglement. A bridge could be engineered to be in a quantum-entangled state with its own structural monitors, so that the moment a microscopic crack begins to form, the entire bridge enters a new quantum state that signals the need for repair long before the damage is classically visible. The line between the quantum and classical realms would not just be blurred, it would become a domain for engineering and design. We would move from being passive inhabitants of a classical reality to active architects of a quantum classical hybrid world, where the strange and the solid coexist, and the laws of physics become a palette for creation. But what if our mastery over the quantum world extended beyond personal devices and materials to weave a new fabric of connection itself? This brings us to one of the most profound technological horizons on the map, the quantum internet. This wouldn't be merely a faster version of the internet we know today. It would be a fundamentally different kind of network, built not on streams of classical bits, but on the spooky linkages of quantum entanglement. The implications for our daily lives, our security, and even our very conception of shared experience would be nothing short of revolutionary. The most immediate and tangible benefit of a quantum internet would be the advent of unhackable communication. Today, when you send a credit card number or a private message over the internet, its security relies on complex mathematical problems that are difficult for classical computers to solve. But a powerful enough quantum computer could crack these codes effortlessly, rendering our current encryption obsolete. A quantum internet solves this problem at its root using the principles of quantum mechanics. The technique is called quantum key distribution. Imagine two people, let's call them Alice and Bob, want to share a secret. Instead of sending a coded message, Alice sends Bob a stream of individual photons, each prepared in a specific quantum state representing a piece of the secret key. Here's the magic. If a hacker, Eve, tries to intercept these photons to read the key, the very act of her measurement will inevitably disturb their delicate quantum states. This disturbance is detectable. Alice and Bob can compare a small part of their transmission over a public channel, and if they see anomalies, they know the line was tapped and they simply discard that key and start over. If there's no disturbance, they can be mathematically certain that their key is secure and use it to encrypt their message. This isn't a stronger lock, it's a lock that shatters and announces an intrusion if anyone even looks at it wrong. For the average person, this would mean a world where financial transactions, medical records, and private conversations could be conducted with absolute, physics-guaranteed privacy, creating a level of trust in our digital interactions that is currently impossible. Beyond perfect security, a quantum internet would unlock a new form of distributed computing power. Just as today's cloud computing allows us to access vast processing resources over the classical internet, a quantum internet would allow us to connect smaller, specialized quantum processors together to form a single, vastly more powerful virtual quantum computer. A researcher in a small university lab could, by tapping into this network, run a simulation of a complex new drug molecule that would be far beyond the capacity of their local equipment. This distributed quantum cloud would democratize access to quantum computation, accelerating breakthroughs in science and engineering. We could see a global collaborative effort to model climate systems with unprecedented accuracy, or design entirely new materials with tailored properties by pooling the quantum resources of the entire planet. This transforms the quantum computer from a rare, centralized behemoth into a ubiquitous utility as accessible as electrical power, fueling innovation in every corner of the globe. Perhaps the most mind-bending implication, however, moves beyond practical applications into the philosophical realm, the concept of a genuinely shared reality. Our current internet shares information, copies of data. I send you a photo and you receive a perfect duplicate on your device, but the original remains with me. Quantum networks could enable the sharing of quantum states themselves through a process called quantum teleportation. This doesn't mean physically teleporting an object, but rather transferring the exact, full quantum information of a particle from one location to another, with the original state being destroyed in the process. Now extend this idea. What if we could create a network where two or more quantum sensors are permanently entangled? Imagine a future where you and a friend on opposite sides of the world each have a quantum virtual reality interface. You could both touch a shared virtual object. Because your interfaces are entangled, the sensation of resistance and texture you feel would not be a simulated approximation. It would be generated by the same quantum state. Your experience of the object and your friend's experience would be intrinsically linked, two sides of the same quantum coin. You wouldn't be interacting with separate copies of a reality. You would be participating in a single, non-local experience. This challenges our deepest notions of individuality and separation. Today, we infer that we share a reality because we can communicate our experiences and find agreement. But a quantum network could create a platform where information and experience are fundamentally inseparable from their transmission. A piece of data wouldn't be sent from A to B. It would simply exist in a state that encompasses both A and B simultaneously. This could lead to new forms of art, collaboration, and social interaction that are based on a visceral, quantum-level connection. While this may sound like science fiction, the fundamental principles are being tested in labs today over short distances. Scaling this to a global network is a monumental engineering challenge, but its successful realization would not just be a technological leap. It would be a philosophical one, offering a tangible demonstration that the universe is far more deeply interconnected than our classical senses have ever allowed us to perceive. Yet, for all its explanatory power, decoherence ultimately addresses the how rather than the why. It masterfully describes the mechanism by which the quantum world appears classical to us, but it doesn't explain why the underlying quantum reality is structured in such a way that this emergence is even possible. This pushes us toward one of the most profound questions in all of physics: what is truly fundamental? Is the arena of space and time, the very stage on which the drama of decoherence plays out, itself a secondary phenomenon? A growing number of theoretical physicists are now exploring the radical possibility that our familiar four-dimensional continuum might not be the bedrock of reality, but rather a large-scale illusion that crystallizes out of a more primitive, non-spatial quantum foundation. This idea finds powerful expression in theories like loop quantum gravity. In this framework, the smooth fabric of space-time is not a given. Instead, it is composed of discrete, quantized units, tiny loops or networks of gravitational field lines. Think of it like a digital photograph. When you look at a high-resolution image on a screen, it appears smooth and continuous. But if you zoom in to the maximum, you discover it's actually composed of individual pixels. Loop quantum gravity suggests that space itself is pixelated. At the incredibly small Planck scale, space is not smooth and continuous but granular, a vast web of interconnected nodes. What we experience as the continuous geometry of the universe emerges from the collective properties of this web, much like the smoothness of a fabric emerges from the weaving together of individual threads. In this view, decoherence is not just a process that happens within space. It is a process that might be crucial for the very emergence of space-time from a more fundamental, pre-geometric reality. The transition from quantum fog to classical clarity could be intrinsically linked to the process by which these discrete quantum grains of space become entangled in such a way that they weave together into the smooth, continuous fabric we navigate every day. String theory, another candidate for a theory of quantum gravity, offers a different but equally mind-bending perspective on emergence. It proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. The different vibrational patterns of these strings give rise to the different particles we observe. Crucially, string theory requires extra spatial dimensions beyond the 3 we experience, often positing 10 or more dimensions in total. Our 4-dimensional space-time is then seen as a brane, a kind of membrane floating within a higher dimensional bulk. The force of gravity and perhaps other phenomena might leak between branes. In this context, our entire universe, with its definite properties, could be the result of our specific position on a particular brane. The laws of physics we consider fundamental, including the very dimensionality of our world, might be a low-energy accident, a frozen relic of a much more symmetric, higher-dimensional reality. Decoherence in this picture would be the process that not only selects classical states but also helps to stabilize our particular brane configuration, making our specific version of space-time feel robust and real. These theories force us to reconsider the nature of existence itself. If space and time are emergent, then what we perceive as the flow of time, the relentless march from past to present to future, might also be an illusion born of this emergence. From the viewpoint of the fundamental, non-spatial quantum reality, there may be no such thing as now. The entire history of the universe, from the Big Bang to its final state, could exist as a static, 4-dimensional block. Our subjective experience of a flowing present could be a consequence of our macroscopic, classical perspective, a phenomenon deeply tied to the persistent process of decoherence that continuously creates a consistent, single now from a vast landscape of quantum possibility. This doesn't make our experience less real, but it suggests that our perception of reality is a highly processed, classical summary of a far stranger and more complex underlying truth. So, where does this leave us in the search for what is truly fundamental? The journey from Schrödinger's cat has led us to a breathtaking inversion of our classical intuition. We started by trying to understand how the definite emerges from the indefinite. Now we are confronted with the possibility that the definite world of objects in space and time is not the foundation but the surface. The solid ground beneath our feet, the vast expanse of the cosmos, and the arrow of time itself may all be secondary, collective phenomena. The truly fundamental reality might be a realm of pure quantum potential, a domain of relations and probabilities where concepts like where and when have no meaning. Decoherence, then, is not merely the mechanism that creates our classical world. It is perhaps the very process through which the universe forgets its own deepest, most fundamental nature, giving rise to the stable, tangible, and yet ultimately derivative reality we call home. While decoherence provides a compelling and experimentally verified mechanism for the emergence of our classical world, it is crucial to recognize that it is not a complete theory of everything. It describes the how with remarkable clarity, but several profound whys remain stubbornly unanswered. These open questions probe the very edge of our understanding, suggesting that our current picture, for all its power, might still be missing some fundamental pieces of the puzzle. One of the most significant unresolved issues is the precise role of gravity. Our two most successful theories of physics, quantum mechanics and general relativity, describe the universe with breathtaking accuracy, but they speak different languages and have proven notoriously difficult to reconcile. Decoherence is a process firmly rooted in standard quantum theory, which treats space and time as a fixed, unchanging stage. General relativity, however, tells us that space and time are dynamic, curved by the presence of mass and energy. Roger Penrose's conjecture that gravity itself might be the trigger for an objective wave function collapse is a bold attempt to bridge this gap, but it remains unproven. The central question is this: when a massive object enters a superposition of positions, does it create a superposition of different spacetime geometries? And if so, is that configuration stable? We simply do not know. It's possible that a full theory of quantum gravity will reveal that decoherence is not just caused by photons and air molecules, but is also profoundly influenced by the gravitational field of the object itself. Until we can perform experiments that probe quantum effects at a scale where gravity becomes significant, this will remain a tantalizing mystery, a silent question mark hovering over our most elegant explanations. This leads directly to another deep philosophical divide: the question of whether the wave function's evolution is truly unitary, as the many worlds interpretation insists, or if there is a genuine non-unitary collapse. Decoherence brilliantly explains why a superposition appears to collapse from our perspective, but it doesn't require the other possibilities to vanish from reality. They simply become inaccessible. This is a unitary process. However, theories like GRW propose that collapse is a real, physical event, a non-unitary modification to the Schrödinger equation that literally erases all but one outcome. The difference is monumental. In one view, the universe is a vast multiverse where every possibility is realized. In the other, it is a single, definite history. While decoherence makes the many worlds view much more palatable by explaining why we don't see the other branches, it doesn't definitively rule out objective collapse. The effects predicted by collapse theories are incredibly subtle, and designing an experiment sensitive enough to detect them is a monumental challenge. So, we are left with a choice between two radically different visions of reality, with decoherence serving as a powerful tool for both, but not yet a referee that can declare a winner. Underlying all of this is perhaps the most fundamental question of all. What is the quantum state? Is the wave function an ontic state, a direct representation of reality itself, or is it an epistemic state, merely representing our knowledge or information about a system? If the wave function is ontic, then a particle in a superposition is genuinely, physically in multiple states at once. Its blurred existence is a real property of the world. If, however, the wave function is epistemic, then the superposition is not a statement about the particle's state, but about our ignorance of it. In this view, the particle might always have a definite position and other properties, but the wave function captures our incomplete knowledge, much like a probability distribution in a game of chance. Decoherence fits comfortably within the ontic view, as it describes the physical process of environmental monitoring that selects a preferred basis. But it can also be incorporated into certain epistemic interpretations, where it explains how our information about the system becomes correlated with the environment, updating our knowledge. Experiments have been devised to test these ideas, and so far they lean toward the wave function being ontic. Yet the debate is not fully settled, and it forces us to confront whether quantum mechanics is a description of the world as it is, or merely a tool for predicting what we will observe. Therefore, we must be honest about the limits of our current knowledge. Decoherence is a towering achievement that solves the practical problem of the quantum to classical transition. It demystifies measurement, banishes the need for conscious observers, and provides a robust physical mechanism for the emergence of the world we see. It is a crucial piece of the puzzle, but it may not be the final piece. It tells us how the fog settles, but not why the landscape of quantum possibilities exists in the first place, or what the ultimate nature of that landscape truly is. These open questions are not signs of failure. They are the guiding lights for the next generation of physicists. They remind us that our journey to understand reality is far from over, and that the most profound discoveries often lie just beyond the boundary of what we currently believe to be true. These mind-bending concepts have not remained confined to physics textbooks. They have exploded into our collective imagination, finding a vibrant and sometimes chaotic life in popular culture. While the mathematics of decoherence may be complex, the core idea of multiple realities and the power of observation is irresistibly compelling. Perhaps no recent film has captured the spirit of the many worlds interpretation, with its endless branching, more vividly than Everything Everywhere All at Once. The movie presents a universe where every possible choice spawns a new reality, and the protagonist, Evelyn, learns to tap into the skills and memories of her infinite alternate selves. This is a beautiful, if exaggerated, metaphor for the universal wave function. The film doesn't show decoherence as a quiet fading, but as a chaotic jumble of possibilities that Evelyn must learn to navigate. Her journey toward a measure of peace mirrors the idea that while all branches may exist, our experience is singular. Our consciousness is effectively trapped on one path, finding meaning not in the infinite possibilities, but in the specific choices we make within our own timeline. On a more intimate scale, the indie thriller Coherence offers a chillingly realistic portrayal of what might happen if the barriers between branches maintained by decoherence were to temporarily break down. During a dinner party on a night when a comet passes overhead, the characters find themselves slipping between incredibly similar yet distinct parallel realities. The genius of the film is that it visualizes the terrifying consequence of a failure in decoherence. The environment, the houses, the street, the people, are nearly identical, but subtle differences creep in. The characters' attempts to communicate and interact with their counterparts from other branches lead to paranoia and chaos, a direct illustration of what happens when quantum interference is not suppressed. The film serves as a powerful narrative on the importance of environmental isolation. In a perfectly decohered world, these branches should be forever separate, but Coherence explores the horror of what happens when that quantum fog lifts and the other tracks become visible, if only for a night. Beyond cinema, the language of quantum theory has seeped into the very fabric of modern self-help and spirituality, often in ways that would make a physicist wince. It's become commonplace to hear phrases like, "You create your own reality," or "Your thoughts collapse the wave function," suggesting that through sheer force of consciousness, we can manifest the outcomes we desire. This is a profound misinterpretation of the science. Decoherence tells us the exact opposite. The environment solidifies reality long before our individual conscious minds get involved. However, the popularity of this idea is incredibly revealing. It points to a deep human desire for agency in an uncertain world. If the universe is fundamentally probabilistic, then perhaps there's a window for our minds to influence the odds. While the physics doesn't support a direct, mystical link between thought and reality, the metaphor can be empowering on a psychological level. The idea encourages focused intention and the recognition that our measurements, the things we choose to pay attention to, do shape our subjective experience of the world, even if they don't alter its objective state. This cultural absorption of quantum vocabulary, from the many worlds of superhero films to the quantum leaping of New Age gurus, signifies something greater than a passing trend. It reflects a fundamental shift in how we see the universe and our place within it. For centuries, the Newtonian clockwork universe suggested a deterministic world, a grand machine where everything was predictable. Quantum mechanics shattered that illusion, replacing it with a reality built on probability, potential, and profound interconnection. The public, often through simplified and sometimes distorted versions of these ideas, is intuitively grappling with this new paradigm. We are collectively trying to understand a cosmos that is not fixed but fluid, not certain but filled with potential. The stories we tell in our movies and the frameworks we use for personal growth are attempts to find meaning and agency within this strange and wonderful new picture of reality, a picture that Decoherence helps bring into sharp classical focus. So we are left with a profound and deeply personal question. If this picture of a branching multiverse, shaped by the quiet process of decoherence, is an accurate description of reality, then who or what are we? Our sense of self is built on the unshakable conviction of a single, continuous narrative, a linear story of choices made, paths taken, and a unique history that defines us. But this new framework challenges that very foundation. It suggests that with every quantum event that becomes amplified, the universe divides, and so do we. There isn't one you reading these words, there is a near-infinite collection of versions, each the inheritor of an identical passed up to a certain point, and each now living out a different future. This forces a radical reconsideration of personal identity. What does it mean to be an individual if your existence is constantly fracturing? The philosopher Derek Parfit explored similar ideas through thought experiments, arguing that what matters for survival is not strict identity over time, but psychological connectedness and continuity. In the many worlds view, this connectedness remains perfectly intact within each branch. The version of you in this branch has an unbroken chain of memories leading right up to this moment. From their perspective, they are the only you that exists, and their story will continue forward uniquely. The other branches are not you in the sense of sharing your present conscious experience. They are more like incredibly similar cousins who diverged from a common ancestor a split second ago. This can be a strangely comforting thought. That terrible mistake you narrowly avoided, a version of you did in fact experience it, but the version that is you, the one reading this, did not. It absolves you of the haunting weight of what if, because in the grand scheme of the multiverse, every what if is a what is for someone else. But this perspective also carries a potentially terrifying weightlessness. If every possible version of you gets to live out their life, then what is the significance of the choices you make? Does it trivialize our struggles and triumphs to know that for every success in this branch, there is a branch of failure, and for every moment of joy, a branch of sorrow? It can feel as though the uniqueness and high stakes of our lives are diluted in an ocean of alternatives. However, one could argue the exact opposite. The significance of your actions is not diminished, it is simply localized. The love you feel for your family in this branch, the project you pour your energy into, the kindness you show, these things are utterly real and meaningful within the reality you inhabit. The existence of other branches doesn't make this one any less vivid or important to you. In fact, it might heighten the value of your specific, subjective experience. This is the only thread of reality you will ever know. Its texture, its pains, and its joys are yours alone to experience within this continuous stream of consciousness. This leads us to a new way of thinking about responsibility. We often frame morality in terms of the consequences of our choices, but if every choice is made, how do we assign blame or praise? The answer may lie in focusing on the decision-making process itself rather than the outcome. A good decision made with careful thought and ethical consideration is a good decision in every branch where it is made. The fact that a random quantum fluctuation might lead to a bad outcome in another branch doesn't negate the quality of the intention in this one. Your character is defined by the choices you are disposed to make. In a branching universe, you are, in a sense, the sum of all your decision-making inclinations across the multiverse. Cultivating wisdom, empathy, and courage in this branch means that a greater proportion of your branching selves will be equipped with those tools. Responsibility shifts from being solely about controlling outcomes to about shaping the kind of decision-maker you are in the one reality you call home. Ultimately, the meaning of life in such a cosmos becomes not a grand, universal answer, but a personal assignment. There is no single, predetermined purpose handed down from the universe because the universe is busy realizing every possible purpose. The meaning of your life is the meaning you create and discover within the branch you inhabit. The project of your life, to learn, to love, to build, to understand, is no less noble or urgent. The branching multiverse doesn't strip life of meaning. It presents a cosmos of unimaginable richness and offers you a single, precious thread to cherish and navigate. The awe we feel when contemplating the stars is now matched by an awe for the inner cosmos of possibility and the profound, singular journey we are each undertaking through it. And so we arrive at the end of our journey, a path that began with a cat in a box, suspended between life and death, and led us to the quiet, pervasive hum of the environment. We have witnessed the profound puzzle of the quantum world, where particles exist as clouds of possibility, and grappled with the mysterious moment of measurement that seemed to force a choice. We explored the radical interpretations offered to solve this riddle, from the pragmatic surrender of the Copenhagen view to the breathtaking cosmic extravagance of the many worlds interpretation. But it was decoherence that provided the elegant and powerful bridge, the tangible mechanism that explains the emergence of our solid classical world. It showed us that the collapse is not a dramatic event triggered by consciousness, but a gradual, inevitable fading of quantum possibilities as information leaks into the environment, a process as natural as rain falling on a pond, shattering a perfect reflection into a blur of ripples. While decoherence may not answer every deep metaphysical question about the nature of consciousness or the ultimate reality of the wave function, it provides something immensely valuable, a robust, testable, and physically intuitive framework. It demystifies the quantum to classical transition, grounding it in the countless, random interactions that happen every moment. It reassures us that the moon is indeed there when we are not looking, not because of a potential observation, but because it is continuously observed by the sunlight and cosmic radiation bathing its surface. This framework doesn't just solve a century-old problem in physics. It fundamentally reshapes our understanding of reality, revealing that the definiteness we experience is not a given, but a dynamic, emergent property born from interaction and entanglement. As you go about your day, surrounded by the seemingly solid and predictable world, I invite you to ponder this: the device you're holding, the chair you're sitting on, the very air you breathe. All of it is constantly participating in this grand, silent dance of decoherence, each interaction quietly reinforcing the reality you perceive. So the next time you make a choice, big or small, consider the infinite potential that existed in the moment before you decided. Your path may feel singular and certain, but it emerged from a quantum fog of possibility, shaped by the same physical processes that govern the entire cosmos. The greatest adventure now lies ahead, in the technologies we will build by learning to harness these very principles. What new realities will we create when we learn to dance with decoherence rather than simply be shaped by it? The future, like a quantum state, remains a superposition of incredible possibilities, waiting for our curiosity to collapse